Welcome to this explainer, where we're going to gently unpack the quiet, repetitive magic of the batteries that power our daily lives. You know, if you're a college student balancing classes, late-night study sessions, and, well, trying to have a social life, you already know that staying powered up is absolutely essential. But today, we aren't going to look at this like some dense textbook chapter you have to memorize for an exam. Instead, we're just going to take a calm, curious look at the invisible chemical cycles happening right inside our backpacks and on our desks. Look at the device you're using to experience this explainer right now. Eventually, its screen is going to go dark. It dies. And yet, we simply plug it into a wall, wait a little while, and it breathes right back to life. We don't even give it a second thought, do we? But that simple everyday act is actually a massive triumph of modern engineering. It's an amazing cycle of renewal that happens entirely out of sight.
And this everyday phenomenon isn't just some abstract concept confined to a chemistry lab. It's practically the foundation of our modern lifestyle. The fact that certain chemical reactions can run in reverse is exactly what gives us the freedom to move around, to study at a coffee shop, to travel, and to connect with each other on our own terms. It's portable energy, ready exactly when we need it. Okay, let's dive into this by broadly classifying the batteries we use. In the engineering world, we generally divide commercial batteries into two main categories, primary and secondary. Think of a primary battery as a one-way street. These are the alkaline batteries in your TV remote or the dry cells in a flashlight. Once their active chemical components are used up, well, the journey's over. You have to discard them. But secondary batteries, those are a brilliant two-way street. They're designed specifically to be recharged and reused. It's really interesting when you contrast a primary cell's one-way reaction with the beautiful, reversible cycle of a secondary cell. On one side, we see a simple discharge, but on the other, you have arrows pointing in both directions. When the battery is providing power, it's discharging, but when you apply an electrical current in the opposite direction, the arrows reverse. The inactive materials are literally pushed back into their active state, ready to go all over again. To define it simply based on our source material, a secondary battery acts like two completely different devices depending on what you're doing. When you're actually using your device, the battery is a galvanic cell, meaning it's spontaneously pushing out energy by converting chemical energy into electrical energy. But the moment you plug it into the wall to charge, it transforms into an electrolytic cell. It uses that outside electricity to force the chemical reaction to run backward, pulling the energy right back in.
Section 1. The heavy lifter, lead-acid.
Let's start with the big ones. Inside a reliable lead-acid storage cell, which is a design rooted way back in 1859 if you can believe it, you have a grid of lead acting as the anode, and a grid packed with lead dioxide acting as the cathode. These plates sit alternatingly in a bath of sulfuric acid, which acts as the electrolyte. It's heavy, it uses strong acid, but man, it is incredibly robust.
So, the crucial point here is that while we rarely see them, these robust storage cells are basically the invisible guardians of our modern world. They're the 12-volt batteries that seamlessly start our car engines. They act as massive, uninterruptible power supplies, or UPS systems, that keep life-saving hospital lights on during grid failures. They power railway systems and telephone exchanges. Basically, they do the heavy lifting so we don't have to. Now, instead of stressing over complex redox equations or memorizing chemical formulas, because nobody really wants to do that right now, just think of this as a patient cycle of giving and restoring. When a lead-acid battery gives you power, both the lead and lead dioxide plates slowly convert into lead sulfate, and the sulfuric acid becomes more dilute. The materials are transforming to give you power, but when you plug it in, the electrical energy forces the lead sulfate back into lead and lead dioxide, regenerating the acid. It resets the stage perfectly.
Moving on to Section 2. Daily power. Nickel and Li-ion.
Scaling down from hospitals and cars to the smaller marvels in our pockets, inside the compact, sturdy casing of a nickel-cadmium or NiCad battery, you'll find a cadmium anode and a nickel oxyhydroxide cathode, separated by a potassium hydroxide electrolyte. And here's a cool detail. Because the overall chemical reaction here doesn't actually consume the electrolyte, you only need a tiny amount of it. This brilliant design choice reduces the weight of the battery while giving it a long shelf life and making it super durable.
Comparing these chemistries really highlights how engineers choose different designs based on exactly what we need the device to do. A standard NiCad battery gives you about 1.4 volts, which makes it absolutely perfect for sturdy, reliable items like calculators, electric shavers, or emergency flashlights. But modern smartphones and laptops, they demand way more power without adding weight. That's where lithium-ion comes in. Because lithium is such a ridiculously light metal with a high potential, a single Li-ion cell can deliver around 4 volts, giving us the high energy density our modern screens and processors demand.
In fact, in the laptop, tablet, or phone you are using right now, there's a wonderfully elegant process happening. There isn't any metallic lithium inside. Instead, lithium ions are quietly flowing back and forth between layers of porous carbon and a lithium metal oxide. They travel through a polymer gel, peacefully migrating to the negative side when charging and flowing back to the positive side to release power into your device. It's quite literally the heartbeat of your digital life.
And that brings us to Section 3, a peaceful takeaway.
Our sources state it pretty simply. The electrical energy is stored in them in form of chemical energy. Everything we've discussed today, from the massive lead grids starting our cars to the delicate flow of lithium ions in our phones, relies on this simple, invisible cycle. Energy is constantly and faithfully renewing itself in the background of our busy, demanding lives. It's stored safely as chemistry, just waiting patiently until we need it as electricity.
So, here is the crucial point for today. The next time you plug your dead phone into the wall at the end of a long day of classes, take a deep breath. Just appreciate that quiet, reliable cycle of renewal happening right there in the palm of your hand. It's a beautiful two-way street of restoring energy. And it might even make you wonder, what other invisible cycles of renewal might we be taking for granted in our own lives? Thank you so much for joining me on this explainer, and I really hope this brought a little bit of clarity and calm to your day.